Today we are going to discuss Clapeyron equation. This is a thermodynamic equation derived from second law of thermodynamics. So this is a thermodynamic equation based on the second law of thermodynamics. Most commonly this is used to study the equilibrium reactions between the phases of a single component. We can say this is for one component two phase systems. One component two phase systems. That is, we can use it for solid to liquid equilibrium, or liquid to solid, or liquid to gaseous equilibrium, or solid to gaseous equilibrium, etc. So let us derive the Clapeyron equation. So consider A reversibly gives B. Here A and B are two states or two phases of a single component. So we can say, for example, we can say A is solid and B is liquid. And these two are the two different phases, that is A and B are the two different phases of the same component. Here we are going to consider the equilibrium between these two phases of the single component. We can say the free energy of these two phases per mole are equal. That is, we can write it as GA equal to GB. Here, this is the free energy per mole of the phase A. Free energy per mole of phase A. Same way, this is the free energy per mole of phase B. So at equilibrium, these two are equal. So we can write the difference in free energy of these two states are 0. That is delta G for this reaction equal to GB minus GA equal to 0, since these two are same. Here's the equation: A giving B, GA equal to GB, and delta G equal to GB minus GA equal to 0. If we change the temperature of the system at equilibrium, change of temperature, according to Le Chatelier principle, the entire system will be rearranged. So, if we change the temperature T from T plus dt, that is, we are raising the temperature of the system, then the entire system will be rearranged. That is, pressure P changes from P to P plus dP, and the free energy of each state will be rearranged as GA from GA to GA plus dGA, and GB to GB plus dGB. So here in this new equilibrium, the Gibbs free energy, newly arranged Gibbs free energy of physical state A and B are equal. That means GA plus dGA will be equal to GB plus dGB. Since GA equal to GB, we can write dGA equal to dGB. Now, according to Maxwell's equation, we know 4 Maxwell equations are there, and the Maxwell equation for change in free energy is dG equal to VdP minus SdT. And we can write the change in Gibbs free energy of physical state A and physical state B as dGA equal to VAdP minus SAdt. Same way, dGB equal to VBdP minus SBdt. From this, that is from the equation number here, we can write it as equation number 1 and this 2 and this 3. By comparing equation number 1, 2 and 3, that is dGA equal to dGB, so we can write 2 equal to 3. That means VAdP minus SAdt equal to VBdP minus SBdt. So that is VAdP minus SAdt equal to VBdP minus SBdt. So rearranging this equation, we can write it as VB minus VAdP equal to SB minus SA into dt. So dP minus dt equal to SB minus SA divided by VB minus VA. SB and SA are entropies of the phase B and A, and VB and VA are the volume of the phases B and A. So we can write dP divided by dt equal to change in entropy delta S divided by change in volume delta V. So here delta S is the change in entropy of the phase equilibria. That is, we can say this is the change in entropy of the equilibrium at a particular temperature T. At a temperature T. So we can write delta S equal to Q divided by T. Here Q is the heat transferred during the equilibrium reaction. So we can say this is the heat transferred in a reversible reaction. In a reversible reaction. And T is the temperature. So this equation will be dP divided by dt equal to Q divided by T delta V. So this is the Clapeyron equation. So this is the Clapeyron equation. If we talk about vaporization specifically, Clapeyron equation for vaporization is dP divided by dt equal to delta Hb divided by delta V. Here delta Hb is the heat of vaporization. Heat of vaporization. Same way for fusion reactions, that is for melting and freezing reactions, we can write the Clapeyron equation as dP divided by dt equal to delta Hf divided by delta V. Here delta Hf is the heat of fusion. Now let's move on to Clapeyron equation. Here, this is the integrated form of Clapeyron equation. So this is the integrated Clapeyron equation. Normally, this is used for liquid to vapor conversions and solid to liquid conversions. So, if we consider the conversion of liquid to gas, that is the equilibrium reaction between liquid and gaseous state, we can write the Clapeyron equation like this: dP divided by dt equal to delta HV divided by delta V, that is V liquid minus V gas. Here the volume of liquid is very much lesser than the volume of gas. So we can neglect the volume of liquid if we compare with volume of gas. So we can rewrite this equation like this: dP divided by dt equal to delta HV divided by V gas. Since VL is very less than VG. Here this is the volume of gaseous substance. So we can use the ideal gas equation PV equal to RT here. That is V equal to RT divided by P. If we substitute this value here, then we will get dP divided by dt equal to delta HV divided by RT into P. Now we have the equation dP divided by dt equal to delta HV into P divided by TRT. Or we can write it as dP divided by dt equal to delta HVP divided by RT square. Now I am going to bring the P term into the LHS side, that is dP 1 by P dP divided by dt equal to delta HV divided by RT square. Here we can write it as d ln P divided by dt equal to delta HV divided by RT square. So now I am going to bring the dt term into RHS side. So I'll get d ln P equal to delta HV divided by RT square dt. So now we are going to integrate the equation d ln P equal to delta HV divided by RT square dt. So integral d ln P, we can take the constant term out, that is delta HV divided by R into integral 1 by T square dt. Here integral d ln P equal to ln P and equal to delta HV divided by R. Here 1 by T square we know. Standard equation for x raised to n dn equal to x raised to n plus 1 divided by n plus 1. See, here it is t raised to minus 2 dt. So we can write the answer as t raised to minus 2 plus 1 divided by minus 2 plus 1. Here we will get t raised to minus 1 divided by minus 1. That is the answer is 1 by t minus 1 by t. So ln P equal to delta minus delta HV divided by R into 1 by t plus C. C is the integrated constant. So we will get the integrated equation like this: ln P equal to minus delta HV divided by RT 1 by t plus C. It is in the form of mx plus C. So we can draw a graph like this. X-axis is ln P and y-axis is ln P and x-axis is 1 by t, and here negative values here, so we'll get an inverted graph like this, and the slope is delta minus delta HV divided by R, and the intercept is C. We can integrate this equation by applying some integral limit from pressure P1 to P2, and the temperature is from T1 to T2. Then we'll get the answer like this. Integral, that is integral P1 to P2 ln d ln P equal to delta HV divided by R into integral T1 to T2 1 by T square dt. So we'll get answer like this. Here we'll get ln P, that is ln P P1 to P2, and here we'll get minus delta HV divided by R into 1 by T from T1 to T2. That is here ln P2 minus ln P1 equal to minus delta HV divided by R into 1 by T2 minus 1 by T1. So we can write it as ln P2 by P1 equal to, we can remove this minus sign by reverse this term, that is delta HV divided by R equal to 1 by T1 minus 1 by T2. If we cross multiply the term inside the bracket, we'll get ln P2 divided by P1 equal to delta HV divided by R into T2 minus T1 divided by T1 T2. This is the Clapeyron equation. Same way we can write the Clapeyron equation for sublimation also, that is solid to vapor state. So this is all about Clapeyron equation.